So good evening, everyone. So today, let's discuss about quantum key distribution, which is also called quantum cryptography. So let's see why do we need quantum cryptography? Because we already have classical cryptography. What are the flaws in classical cryptography? And let us also see some protocols like BB84 protocol, which you will see in the later part of the slides. And let's also like check out the Qiskit implementation of quantum key distribution. And yeah, like with that we will conclude with the Qiskit code. Let's conclude this session. So how did it all started? You can see the evolution of communication over the past a few decades, I would say. So back then we used to communicate with pigeons and all. Pigeons used to fly from one place to another place to send the information. Now we have evolved to such a state that like we just need to take out our cell phone and put out the message out there. That's it. Like we have WhatsApp, we have Twitter, Facebook, Instagram, Snapchat. So there are a lot of platforms where we don't need to move from one place to other place. So it all started with the internet, right? So what is the main goal of communication? The main goal of communication is to send information from one person to the other person, or from one place to the other place. So that is the main idea. And also I want to add that the information is physical. For example, like what are pigeons, what did pigeons carry? Pigeons used to carry papers, or like the information that is written in the paper. So whatever you take, so the information is physical, is what people proved. So that's how it works. Information is physical. You might think that like I'm just texting it over the internet, but like where is the physical quantity? But that's not how it works. There is a lot happening behind the scene. When you text something, it's not like I'll just text it here and like someone is going to see that. So yeah, like let's see how that works. And let's also as I discussed, let's also see the Qiskit implementation. So without further delay, let's quickly go. So classical cryptography or classical communication works with classical bits, right? So we send information over the classical channels. So basically there are two main branches in classical cryptography. One is secret key cryptography, and the other one is public key cryptography. So secret key cryptography is the traditional method which we like daily use in our day-to-day lives. So which ensures that both the parties need to have the shared secret key before we send the information, right? So for example, there are two persons, one is in Chennai and one is in Bangalore. So before we need to send an information from Chennai to Bangalore, both of the persons need to have the shared secret key, so that they can decrypt the information once he receives. So there are disadvantages for shared secret key. Like sending having the shared secret key beforehand might be difficult. It's not that easy. Like you need to create the shared secret key, but how are you going to have the shared secret key beforehand? Uh, Even you need to share this secret key over classical channels, right? So how are you going to ensure that the shared secret key is not being hacked by the cyber attacks? So there is another cryptography called public key cryptography, where there is no guarantee that there is no guarantee that both of the parties should have the shared secret key before like before sending the information. So this I mean I have here is the block diagram of secret key cryptography. You can see that the plain text, and also there are three things in communication. One is encryption of the information, second one is sending the information, and third one is decrypting the information. So any information before sending it to before having that on the communication channels, it should be encrypted so that no one will hack it, or no one will no one will get to know what the information is about. So that we use this shared secret keys to lock it, basically. So no one should know what is the secret key of that particular information. If someone knows the secret key, they can open the lock and then they can know the information, and that is it, you're done. For example, like how do banking system works. So if someone knows your shared secret key, if someone knows the pin to your ATM, they can easily withdraw the amount without your consciousness. So the same happens here. So your message should be encrypted with the secret key, and that secret key should be very very much protected, so that your information is not lost. So for example, I mean, I just added this here. So Alice want to talk to Bob. Okay, and Bob never knows someone is hearing that, right? Like for example, if I'm speaking to someone in Kolkata, and like if I'm giving him some my ATM pin, for example. Okay, so if someone is already hearing that without my consciousness or without my involvement, and he already knows my ATM pin, and it's easy for him to like draw all the money from my account. So it's just a matter of time. So we should be very much ensure that the secured key, the secret key, is not being shared, or someone is not coming in the middle and collecting our data. So that's how cyber attacks also happen. And in India, most of the cyber attacks are on the companies. For example, there is a cyber attack on government website, where we upload our Aadhaar card details, PAN card details, right? In 2018, it was a big cyber attack. Almost 1 billion people, like they have collected all the data with images and all. So we never know, like it's so easy on classical communication channels to hack and to get data to come in middle without your consciousness, and to collect your data. So that's how you sometimes might wonder, how are you getting messages? Like we get a lot of fraud messages. Even I have personally faced this issue. Like some guy called me from USA. I didn't even know he got all my contacts. Like he called so many members through my contacts. And the one I wondered, uh, people called me back and they were asking, why did you call me? But I never called them. That dude hacked my phone, and he got all my contacts, and he was calling from my phone. But I didn't call them, and I'm receiving the phone calls from my contacts asking that, why did you call me? So like I was quite bizarre at that moment, but I have experienced this. So I'm telling you, I want to make sure that classical communication is not that secure, and like it's easy to hack. So yeah, so here comes the quantum thing. So why do we need quantum? Because to have the security, and no one can like come into the middle and learn the key, and then they can like go out and haha, I have all your data. You cannot do if it is data driven world, right? We are all living in a data driven world. So if they have your data, that is it. I guess you don't they have everything about you. So quantum assures that no one is coming into the middle and stealing this data, and at the same time, it makes current public key cryptography systems obsolete. Means like it's a lot advanced than the current public key crypto systems, which quantum will make these as old, and quantum will like will set a platform for itself. So yeah, let's move further and let's understand what is quantum key distribution or quantum cryptography. So the let's narrow down to the basics again. So what is communication? Like like Alice and Bob are two parties, and Alice wants to send information to Bob. So that is the our main goal. So for example, there are two channels. Alice and Bob. Alice can send messages to Bob. One is classical channel and one is quantum channel. So in our case, let's put a third party called Eve in the middle, and let's think that she has both access to both quantum channel and classical channel. Okay, in classical channel, she can easily get track of your data while you're transforming while Alice is transforming her message to Bob. Let's see how she cannot get track of the data when it is transferred through a quantum channel, which is quantum communication. Uh, it will basically happen through photons and photon detectors. Like, let's get into that in the next slides, but this is the basic idea. So Alice wants to send message to Bob. We involve third party here to check if by chance if some other third party is coming in middle, Bob and Alice both will know that some third party has come into the middle. If Eve is stealing the data, if Eve wants to learn the secret key, both Alice and Bob will get to know that Eve is doing something in the middle, and they can destroy the data too. So let's see how the quantum cryptography and quantum communication works. So there is this protocol called BB84 protocol, which is which we can call not an algorithm, but it's kind of an algorithm in quantum cryptography. So it is proposed in 1984 by Bennett and Brassard, and the name comes from there. As you can see that the first letter of Bennett and Prasad, and 1984, so BB84. So the idea is to encode every bit of the secret key into the polarization state of the single photon. It's like each photon will be encrypted with this. Each photon will be basically encrypted. So why did you take only photons? Because when you measure the photons, the information will be lost. So if, for example, Eve wants to measure the photons that are encrypted, so for example, Eve is decrypting the encrypted photons. So once she decrypts the photons that Alice sends, then the information is lost. Then she cannot again she cannot again build the photons, and she cannot again send to Bob. So Bob will never receive the same state that Alice wants to send. So Alice can contact Bob over the classical channel and tell Bob the actual answer, but Bob will get the opposite answer or the other answer, and then Bob can easily know that somewhere a mistake had happened, and Eve or some other third party has come into the middle, and the data is lost. But in classical channel, it's not like that. You never know, until and unless some action is done onto your account. For example, before the cyber attacks happen, the companies do not know that some attack is going to happen on the company, right? On the if you know that in advance, you will be prepared. You will prepare something against that to happen. So classical communication makes that, like, it will let you know that something is going to happen on your data, so you can change the data immediately, so that you will be secured. So let's see how that happens. Let's elaborate BB84 protocol. So basically the idea is every photon, the secret key will be encrypted on every single photon. For example, if the secret key is of 10 characters, so we'll use 10 photons to each photon will be encrypted with the each character, right? So as I have already mentioned, if Eve or some other third party comes into the middle, and if she measures, the data will be destroyed and it cannot be recreated again. So let us go further and explore BB84 protocol. So the main idea is, like, as I have discussed, the main idea is to encrypt the secret key with the single photon. So we will encrypt that as follows. So Alice encodes zeros into H polarized photons, while unity is into V polarized photons. As you can see in the diagram, so red color ones, vertical and horizontal, like the vertical one with H polarized, and the horizontal one is also V polarized, right? Sorry, yeah. Horizontal one is H polarized and vertical one is V polarized. It can be seen in the red arrows. And there is also another polarization called depolarization and apolarization, which can be seen in the blue arrows, right? So there are total 4 polarizations which Alice can encrypt her messages. So for example, there are 10 bits qubits she want to send to Bob, then she can use these 4 different types of polarizations and encrypt her message. So she will not tell what kind of polarization she used to Bob until and unless he okay, let's get into that. uh, here. So Bob will receive these encrypted messages, and then what Bob will do is Bob will randomly, Bob will randomly measure. Like he knows that there are only four polarizations Alice can probably use. Okay, so Bob will randomly choose whatever polarization he wants. There is nothing like Bob should only choose whatever Alice sends. So Bob will randomly choose whatever that comes to his mind, and then Bob will also measure it. Okay, Bob will measure it, and then Alice will publicly announce the polarization that she used to encrypt each qubit or each information, and then Bob will check if both the Alice and the Bobs uh, both use the same polarization, and they'll check the result of both data. If both data's result is same, then they'll ensure that the communication is secure, right? Let's talk about that here. Yeah. So, for example, Alice wants to send 011010001 to Bob. Okay. So Alice encodes this with D, V. I mean, she'll use these polarizations D, V, V, H, A, H, D. Okay. So, and then Bob will also use some random thing. It's not like C. The third and the fifth one, if you look at the third and the fifth one, fifth rows, so both are not same. So this the first three are related to Alice, and the next three are related to Bob. Okay, so Alice encoded or encrypted the polarizations to D, V, V, H, A, H, D, A. But Bob did not use the same. Bob just randomly used whatever that came to his mind at that moment. But the first one, but Bob and Alice use the same thing. Okay, so this will be communicated uh, over the classical channel, because no one, even if they know that this is the same thing that Alice used, they cannot once they measures it, but they don't know on what basis she encrypted that. We'll get into the basis, we'll talk about what is basis and all of that in the coming slides. But even if they know this key, even if the hackers get to know this key, but they cannot encrypt they cannot get the same data, because we have another thing called basis states. We'll get into that further. So these things, like only if both Alice and Bob measures on the same polarization, we'll check those. So for example, the actual thing that Alice wants to share is 0, and Alice polarized it with D. Okay, now Bob measures it. Bob also polarizes or measures with D, and then if he gets 0, it means that no one in the middle has come and sneaked, or like took the data. And he checks it with everything, like see both V and V. So here he did not take this into account, because he did not use the same polarization. So he knew that he'll not receive the same data, because he's measuring with some other thing. It's like I said something, but he knows that he's using some other thing. So why Bob will not consider this? uh, and here, if you see, both are using V, so that 1 and 1, we get the input is 1 and the output is also 1, so that we ensure that no one has come in the middle and stole the data. Here we ignored, because Alice and Bob are using different polarization states. And here you can see both used H and both also got 0, which means that no one has came in the middle. So it basically BB84 protocol works like that. And there are also other protocols called BB91 protocol and yeah, BB91 protocol, which can also be used. It's also basically the same technique, but they'll use different protocol. It's completely on photons, like they'll use photons, but it's a different kind of protocol. They'll entangle qubits here, but here we did not entangle any qubits. There is no entanglement required in BB84 protocol, but there is another protocol called BB91 protocol, if I'm not wrong, where they use entanglement, and they provide the technique is the same, but basically they bring in entanglement for for safer communication and for strengthen strengthen the basics basically. So uh, so that is what basically quantum cryptography is. Like the main idea is this. So Alice and Bob are wants to Alice wants to send some message to Bob, and we created Eve in the middle because we are ourselves creating a third party to check whether our protocol is correct or not. So we do implement the same thing in Qiskit and check how it is working. We can literally uh, compare both information that is in this slide. We can compare both the information using Python and using Qiskit QKD, quantum key distribution, and let's see how that happens in the coming in the coming slides. I'll also walk you through the Qiskit implementation on Google Colab, and like maybe there you can visualize how it's working, and you can also see the code. So it's again the same. So basically what happens is Alice prepares a qubit in plus state. Okay, that is in plus state is 0 in x basis, and Bob measures in x basis. So it ensures that Bob should also measure 0, right? Because Alice prepare that in in plus state, which means 0 in x basis. So if Bob measures it, it is mandatory that he also should receive 0. He shouldn't receive 1 or something like that, because there is nothing happening in between. If there is something happening in between, like if some Eve or some other third party comes in between, and if she steals the data, Bob will not get 0 as an output when Bob measures the data. He'll get some other thing. Yeah, let's see that here. Yeah, so when Eve tries to measure this qubit, so the difference between this diagram and this circuit, yeah, this circuit and this circuit is Eve came in middle and she measured the data, right? She measured the H qubit. So she measured and she tried to get the data, and she sent the data to Bob because it's not she's trying to play smart, and she's thinking that Alice sent the information, so let me get the data and send some information to Bob, and Bob will think, okay, this is the right information Alice sent me. So but that's not how it works. See, when Eve came in middle and measured the data, when measured the qubit, the whole output changed. So that now the probability of Bob measuring 0 has become 50-50. Like before, it was totally 100. It's mandatory that Bob should only receive 0 because Bob is also measuring in the same basis. But after Eve coming in middle, and after Eve, after Eve playing smart, now the probability of Bob measuring 0 has narrowed down to 50%. So now by like this we can know that someone has came in middle and someone has stole our data. So but in quantum communication, it's not like this. This is not how it works in quantum communication. It's a complete different ball game, and you never know if someone is stealing your data. But quantum communication ensures that Bob and Alice both will know if someone has come in middle and someone has come in middle and tried to steal their data. So I'll walk you through the steps, the 5 steps that Qiskit follows, implementing the quantum key distribution protocol. But before that, I just want to ensure if everything is, if everything is clear up till now. Like, can you just, unmute yourself and say yes or something so that I can, or any doubts if you have, that would be great. I can address. So
it's clear. You can move on.
yeah, thanks. Okay, so there are basically 5 steps Qiskit follows to implement the quantum key distribution protocol or quantum cryptography. So the thing is, Alice chooses a string of random bits. Like it's completely random. I mean, that's how it that is not how it works in real life, but Qiskit takes just want to choose it works like that in Qiskit, like we choose a random bits, and then it also applies a random basis to each bit. Like for example, 1 should be in Z basis and X will be, like 0 will be in X basis, and it will just choose a random basis for each bit. So and Alice also will keep these two as secret and private to herself. She'll not share the random bits and at the same time the basis to Bob. So our main aim is to send these random bits 1001, all of this, to Bob without the information being lost in the middle, or without a third party coming in between and stealing these bits. For example, we can take these bits as the like banking, your account number, or like your PAN card, or which is something very important, and you don't want this to get lost, because you are if you use classical, if you use classical communication, there are chances that this information might be lost. So but quantum communication ensures that if someone comes into the middle, it will make sure that both the parties, the sender and the receiver, will know that someone has come in the middle, and someone has tried to steal your data. And we have already seen that in BB84 protocol, how it works. So Alice has random bits, and Alice also has choose some random basis for each bit. Basis in the sense, like she'll measure those bits in that particular basis. Only then Bob will get the same same input. Like for example, if Bob if one is there, like I have encoded 1 into a qubit, and if Bob measure with Z basis, if Bob measures that in X basis, he'll get some other answer. He'll not get 1. So it's like a security system. Like if you do adding a security to your message, like if you don't have this basis state, then it's completely classical. So here comes the quantum advantage. You can choose the basis state for yourself. Like it can be completely random, or you can choose a particular basis state. It's completely up to you. But in Qiskit, we choose a random basis, and then Alice wants to send these random bits to Bob. So the second step is Alice encodes each bit to a string of qubits. For example, 0, 1, plus or minus. So she'll choose these at random, and she'll encodes each bit to these each random bit to these bases. And then she'll say these 1, 0, plus, minus, the one that she gets at random to Bob. So she'll share this message to Bob. She'll not share the original message to Bob. She'll encode this in each basis, and then she'll get something at random, and then she'll share this message to Bob. So now Bob receives the string of qubits. I mean, this like 1, 0, which Alice created, and then Bob measures each qubit at random. For example, Bob has received this 1, 0, plus, and all of that, and then Bob will measure this state or this qubits at random using a random basis. Sorry. Alice has prepared a random basis which starts with ZZX, but Bob is measuring it in XZ. He chose some random basis, and Alice chooses some random basis, and both are not same. So let's see how Bob will end up with the same 1001 message without knowing these random bases and without sending the original message. So I hope things are clear as of now. So, and also Bob will not share the results with Alice in through the classical communication channel. He'll keep the results to himself, private. So Bob and Alice will then share the basis they use for each qubit through publicly. So for example, Alice used ZZX, ZXXX, but Bob used XZZX, and then they'll get to know what basis state each of them used. For example, if the third basis, no, the fourth, yeah, the fourth basis state of Alice and the fourth basis state of Bob are both same. So Bob should definitely get a zero, right? Because the fourth, one, two, three, four, yeah, the fourth encrypted message is zero. So Bob should get a zero when he measures it. When he measures, yeah, when he measures it. But if Bob didn't get zero, then it is quite sure that someone has come in the middle. And to make these, like to make this thing, this protocol very sure, Bob keeps on changing the qubits, like keeps on changing the basis state. For example, he used x z z z x, but he can change it. He will keep on changing the basis state and compare the result that he gets with the original result. So finally, Bob will end up with the with the information that Alice want to send, and he'll and the shared key will be only those uh, bits where Alice and Bob has chosen the same basis. For example, the shared key can be the fourth one is zero. So the shared key can start with zero, and both of them will compare the results. Both of them will, tell each other the basis state that they used, and then that that message can be the shared secret key, and this cannot be known to any person, because only these two know the basis state that they have measured in. So no other guy can come in, and they can never know the secret key, even if they want to know. uh, uh, Here, the fourth thing is zero, because the four here it is z, and here also Bob also measured it in z basis. But some other guy can use some other basis, like for example uh, the fourth qubit he wants to measure, he is using in x basis. Let's think he's using in x basis, and he'll end up with the some different answer. He'll not get zero, and he might think that that is the real thing that Alice is sending, and he'll end up with wrong thing, right? Like for example, your ATM pin is 1718. He'll he his output will be 2718. That will not work, right? So that's how quantum protocol secures your ATM pin, secures your data. So let's this I'll come back to this. This is the implementation in Qiskit, like I'll talk about
Sir, I have
while.
a question. Sir, I have a
Yeah,
question.
yeah, please,
Uh,
please, please.
Sir, how Alice and Bob will share the bases? Like, if they
Yeah,
share
it's
the
public.
bases,
Ah,
then
yeah, yeah, yeah,
sir, if they
please.
share the bases, then that basis can be hacked by someone, and that person can decode the message.
You are saying that this basis, right? Z Z X X X X.
Yeah, like how
Yeah, but
Alice will
no,
convey this
but
basis to Bob.
yeah, but even if they know the basis, they will not know this thing, right? Like they'll not know the random bit. I mean, they'll not know the message, right? See, the message and the basis are kept private for Alice. Like Alice will not share the random bit also. Even if he knows this basis, what qubit is he going to measure? Like he'll not have the message to measure, right? What I'm trying. Okay, let me show you the Qiskit implementation so that you'll understand it in a much more. Yeah, what I'm trying to tell is, like, Alice has bits, right? So these bits, Alice will that guy who is coming in the middle, who is measuring it, who has the basis state, will not know these bits. So he cannot measure, like, even if he know the basis, he cannot measure on these things. Like he cannot measure it on zero, or he cannot measure it on one. Maybe like by the end of this session you will get the answer to this. Once I walk you through this Qiskit implementation, maybe you can understand how that works. But if it is not clear by the end, please let me know again. Please raise the question again, like I'll definitely answer it out. uh, like I am just telling that he will not have anything to measure on. Even if he know the basis, he will not he'll not have anything to measure on. What is he going to have on to measure on in the first place? So the basis can be shared publicly. Bob and Alice then share the basic that's how protocol also works, and I'll also walk you through the Qiskit the Qiskit implementation, and we will check it by ourselves how like both Bob and Alice will share the message by sharing the basis states publicly. So yeah, let's see that how that works, and after that, if the thing is not clear, please raise it again. I'll try to explain it in a simpler words. Okay.
And so one thing also,
Yeah,
sir,
yeah.
like as you are using X gate and Z gate, that
Mhm.
means you are using that plus minus basis and 0 1 basis. Sir,
Yeah, yeah.
only these two bases we can use for QKT, or we can use the Y gate also for complex basis.
You can also use Vigate. It's not like you should only use Z and X. But
Okay.
yeah, you can also use that. But Qiskit, I mean, here in the example, they haven't used Vigate, but I don't think that should be an obstacle. You can definitely use it. Let
Yeah,
us
because
also
if you
try.
make a combination of XY Z,
Yeah,
then
it's
it
only,
will be
yeah, it's only,
more
yeah, it's
difficult.
only, exactly. You're right. Only if you use Y, then 2 power 3, it will be 8. If you use only Z, X and Z, it will be difficult. Uh,
Yeah.
I don't think that should be an obstacle. You can definitely use Y, and let's also try using Y and see how that works. Uh, so let's quickly walk. I'll also quickly walk you through the how Qiskit has implemented quantum key distribution. So I have used basically the same 5 steps that are being used here. So let me quickly. Oh, yeah. Let me quickly reconnect it. Yeah, while it is reconnecting. So the step one is Alice generates a random set of bits. So we generate a random set of bits that Alice wants to send to Bob. So this is the information that Alice wants to send to Bob. Okay. So the next step is Alice will encode it on X or Z or even Y. I guess even Y should work, but like Qiskit hasn't mentioned it anywhere. I mean, this is an example, so yeah, like I don't think it should. Y should it should be an obstacle. Like I don't think, but yeah, like let us also check it out. That is a good question actually. Like I didn't even think of it when while using this, but yeah, that is a great question. Let us also, I mean, I can check it out, and I'll definitely let you know. So for now, let us run this piece of code. Yeah. So the first step is to generate a random bit of qubits. So we take it to be 100 here. Like you can, to just to increase the length of the message. So we took 100. You can maybe narrow it down to 10 or something like that. So first we will generate a random set of bits as mentioned. So I'm just using a random seed from NumPy, and then size to be n, and yeah, like the random bits are either 0 or 1. It's like we didn't include any other number just to keep it binary, so it is either 1 or 0. So after generating 100 random bits, so what Alice will do, Alice will encode each bit onto qubit in the X or Z basis at random. So the step 2 is to create that. So we will see how that is basically happened. So we will create a quantum circuit to prepare a qubit in Z basis, and we'll also create a X basis circuit, and yeah, this thing. Yes. So for example, this is Alice basis and this is Alice bits. Okay. So for example, let us think that Alice bit is 0 and Alice basis is 1. So let us I'll quickly run this and I will talk about that. So there is another thing to be noted, that 0 means we are going to prepare it in the Z basis, and 1 means we prepared it in the X basis. Okay, so let us take 0 means this thing, like 0 is the first bit of Alice bits, and 0 of Alice basis. Okay, so yeah, this is Alice basis. So what is 0 of Alice bits? It is 0. And what is 0 of Alice basis? It is 1, right? So let us see whether we are getting the same thing or not. It should be 0 1, right? Yeah. So bit is 0 and basis is 1. So we created a what is this, a method called encode message. We defined it, uh, so that will automatically take your bit. It will prepare, or it will create a circuit for based upon the bit and based upon the basis. So that this is the code for that. I'll also walk you through how this is working, because I have struggled a little bit understanding this. So not to make it complex, so I'll also explain about this. So yeah, so bit is 0 and basis is 1. So yeah, so bit is 0 and basis is 1. So it should be a Hadamard gate. So we should get a Hadamard gate, and and here in the code, if you look at this piece of code, bit, yeah, this one. So that bit should be 0. If bit is 0, then it will create a Hadamard gate. If both bit and basis is 0, then it will not create anything. It will just like you can directly pass the. You don't need to have any circuit or any not circuit. You don't need to have any not yeah, you don't need to have any gate. Basically, you don't need to implement any gate to prepare it into the any basis. So if both bit and basis is 0, you will not have anything. If bit is 0 and basis is 1, then you need to have a Hadamard gate as per the code to prepare it in the X basis, right? So let us run this and check whether we are getting a Hadamard gate or some other thing. Should be 0. Yeah, so we ended up getting a Hadamard gate. That means it prepared it in the X basis, right? So this piece of code ensures that it will automatically create a circuit, and put the bit into that particular basis. So and there are other things, like if both basis and bit is 0, you don't need to do anything. If basis is 0 and bit is 1, you need to put an X gate. And if basis is 1 and bit is 0, you need to have a Hadamard gate. If both are 1, you need to have X and Hadamard gate. We can also try and check it. I mean, we can check it for ourselves. Let us take yeah, maybe 6 and 6 because both are 1. So let us take a sixth information of bit and sixth information of basis. 7. So seventh piece of information, bit is 1 and basis is also 1. So the circuit should be X and H. So let us see whether we are getting X and H. Yeah. So we are getting X gate, and we are also applying a Hadamard gate. So yeah, let us. I mean, I just randomly checked with some other like I just checked whether this is working correctly or not, and it is absolutely working correctly. So for both, for example, bit is 0 and basis is 1, we don't need to have any gate. Yeah, so with bit is 0 and basis is 1, you don't need to do anything. It's nothing. So you can directly pass. So that is what this piece of code, where if basis is 0 and if bit is also 0, just pass it. You don't need to do anything else. If either of this, like if basis is 0 and if bit is 1, then what you will do is, like, you will apply a X gate. Okay, So this works with basis is 0, and this works if bit is 0. Okay, here basis there are 4 cases. Basis is 0, bit is 0 or 1. Bit is 0, basis is 0 or 1. So the upper part works, takes care of basis is 0 and bits will change, like if bit is 1 or bit is 0, then upper part of the code. And then for lower part, it works with bit is constant, like bit is always 0. If basis is changing, like if basis is 0 or basis is 1, then we have created an else. If both bit if bit is 0 and basis is basis is 1, then what you'll do is like you will apply a Hadamard gate. If bit is 1 and basis is also 1, then what you'll do is like you will apply a Hadamard gate with an X gate, right? So well, without further ado, let us go for the next step. So what now Alice has created a basis state and Alice has also encrypted it. So now Bob doesn't know on what basis what basis Alice has encrypted the messages. So now Bob, the third step is now Bob needs to create, or Bob needs to Bob needs to measure it. Bob needs to decrypt it, or Bob just randomly chooses a X basis, like randomly chooses a basis, and then Bob will measure it. Okay. So what is the yeah? So Bob has measured it. Let us see. So these are the. I need to run it again. So after measuring, so these are the results of Bob. So I just randomly, using random in NumPy, I just randomly created a size with a random string with size of 100, and then Bob will measure it. Here is the measured message. Like here is the definition for the measured message. You can check it for yourself when this code is shared with you. When basis is 0, then Bob will measure it in Z basis. When basis is 1, then Bob will measure it in the X basis. So that's how he will measure it. So for example, the first thing is 1, right? So he will measure it in the X basis. When it is 0, he'll measure it in the Z basis. So yeah, I just this piece of code is just like from starting, like first Alice will generate bits, and then it will encode it. It will encode the message in random basis, and then in step 3, Bob will measure the message. So I'll also run this. So here is the printed result of Bob. So this is the result that Bob gets. But the actual thing is what is this? Yeah. So the actual thing is this thing. So this is the ultimate thing Bob should receive. But he randomly measured. He don't know which basis state he has used. So he got this message. Now what we will do is like Bob will keep these results for himself, and now Alice reveals which qubits were encoded in which basis through Eve's channel. Let us see, let us see what Eve can do here. Because we are sending the basis state on which the basis state which Alice has used encoded through Eve's channel. Like we are literally sending it through the hacker himself. Let us think that Eve is the potential hacker here. So we are sending the basis state through Eve's channel itself, and let us see whether Eve can do anything here or not. Okay. So what we will do is like if Bob happened to measure a bit in the same basis, Alice prepared it in it, then it means that Bob result and Alice result should match. Okay. If both are not matching, then there is no use. Like, right? I mean, if Bob and Alice did not, if Bob didn't measured the qubit in the same basis, then we don't need to consider that information. We only need to consider the information that Bob and Alice who have used the same random basis. Okay. So let us we created this thing called random garbage, sorry, remove garbage, where if both are not same, we don't need to consider them. Like for example, Alice, yeah, for example, the random state Alice used is the random basis Alice used is Z, X, and X. The random basis Bob used is X, Z, and Z. So here nothing is matching. Like Z, Z, and X is not equal to X, Z, Z. So we will not consider the output of these three bits when Bob measures it. But when you take the fourth one, so Alice encryption is Z and Bob is also measuring it in the Z basis. So we will consider this message here and we will remove these three messages. I mean these three bits. So that is what we are doing in remove garbage. So that is the definition of remove garbage here. So it will only return the good bits. It will remove the unnecessary bits. Unnecessary in the sense the if Bob and Alice are not measuring it in the same basis, it will remove those output. Okay. So I just randomly I have added everything here just to make everything clear. So first step, Alice generates the bits. Second, it will encode it, or it will like random on a random basis, and then Bob measures it in the random basis. And the fourth one, we remove the garbage. Like we only take those bits where Alice and Bob has used the same basis, and this will be the key. So this will be the Alice key, right? So now what we will do is like finally Alice and Bob will compare the random selection of bits in their keys to make sure the protocol has worked correctly. So Alice has a key and Bob has a key. So we have removed garbage in Alice basis, Bob basis, and Alice bits. Like these are all the parameters of the remove garbage. So we have used Alice basis, Bob basis. Like we compared both bases and we took Alice bits here and here Bob's result, and we have we have Alice key and at the same time we have Bob's key. So here we printed Alice key, right? So here we printed Alice key, but here we printed Bob key. Now what we should how do we ensure both are correct? I mean this no third party has come in the middle and tracked the information is both the Alice key as well as the Bob key should match, right? Only then it makes sense that like nothing has done in the middle. So let us check for ourselves whether both the let us compare the results of Bob and let us compare the results of Alice key and check whether both of them are same or not. If both of them are not same, then we can make sure that someone in the middle has come and someone in the middle has hacked our data. Okay. So finally Bob and Alice will compare the random bits. So yeah, so these are okay. I need to run it again from where. So yeah. So yeah, so Bob sample is this and Alice sample is this. So now let us see like whether Bob sample and Alice sample works. Yeah. So both of them has the same key now. So which by which we can ensure that uh, no one in the middle has destroyed our data. So let us also check for this case where let us randomly put an interruption in the middle. Like for example, let us think that Eve through which we are sending our data has stole our data, and let us see whether Bob's key and Alice key will match or not. Because it should not match, because we are indirectly, or we wantedly putting interceptions in the middle, so both the keys should not match. So let us see whether they are matching or not. So everything is same. The only difference is it works the same. The only difference is in step 2, in step 3, Eve will measure the data. So let us see how that works. So this is all same. Yeah, so here she's measuring the data, but previously there is nothing called measure. So but here Eve is coming in between and Eve is measuring the data. So let us we have created this wantedly to make sure that the outcome of this should be false. So yeah, so here Eve measured the data, and then again Bob got the data and even he measured it. Okay, so the result of both of them is here. So both of their result is mentioned here. So the Bob sample is this and the Alice sample is this. Both it completely worked the same way, but the only thing is Eve came in middle and she measured the data. Like for example, uh, the Alice basis is something like, for example, ZZXX, and Eve came in middle and Eve tried with some other basis. For example, Eve tried with the same basis, let's think, but Eve will not but Bob will not get the same information because Eve came in middle and Eve destroyed the data, and she cannot recreate the same data, and she cannot put, even if she recreated the data, she does not know in which basis she need to put before sending it to the Bob. Okay, so we run this, yeah, so we can check it for ourselves that both the Bob sample and the Alice sample is not same, because Eve came in middle and she measured the data. This in here, in our protocol there is nothing called measure in between anywhere. Like we didn't measure our data anywhere we didn't measure. So here Eve came in middle and she measured the data. So why the data is destroyed? So once the data is destroyed, she cannot create it. So that is the property of quantum. Once you measure the data, you cannot recreate it. So the data is lost. So she measured the data, so the data is lost, and then Bob will not measure the same thing that Alice wants to send it. So why we got false here. So with that, are there any questions, like anything like regarding code anywhere? Anything that you did not understand in the code? Maybe we can speak about that.
Sir, can you share this Python file?
Yeah, definitely. I'll share this in the Discord as well as in the WhatsApp. I'll also share the PPT, and I'll also share some materials regarding quantum key distribution. I'm not able to take the class yesterday and today morning because I'm having my university exams going on. So I didn't have time to spend a lot of time on this. But today I have spent quite time on this, and I prepared it. So definitely I'll share the PowerPoint as well as the Python code. I have also commented. I have also written this comment so that you can understand what's happening in that particular step, and so that it would be better for someone who who didn't listen the class, or who is not in the class. So it works for them as well as who is in the class. So yeah, I'll definitely share this Python file with you. uh, are there any questions, or maybe there are also other protocols as I have mentioned, but I couldn't explore those because I didn't get time, as they were very big. There are research papers about them. So yeah, maybe if you are interested, you can also explore that part, the protocols part. But as of now, that BB84 is the main protocol that people use. People also implemented, and they have also tested. This is not a theory anymore, because people have already tested, and they were success. So yeah, this really worked for them, but not for 100 qubit message. because we don't have those many qubits to, like we don't have really 100 the highest mission we have is only 163 qubits, if I'm not wrong. So they didn't use it for a big they didn't send a big message from one place to another place, but they sent a only small message, like only some 4 qubits or 3 qubits, and then it worked. So yeah, they checked it for themselves, and it really worked. So that is how quantum key distribution works. And yeah, if there are any doubts, even after the class, like for example, while you are going through this notebook, and if you have any doubts, you can definitely put your questions in the Discord group, or in the WhatsApp. We'll be happy to answer them. Yeah, with this I would like to, like conclude, even though it's not a very long call, but that is the main, that is how it works. And that is the implementation. I have also walked you through the implementation of Qiskit, and I don't think anything other than this is required for quantum key distribution, because it is such a niche field, and like there is a lot of research is also going on. It's an application of quantum computing, so it's very niche. And if anyone would like to like jump in, this is the right time for someone to jump in here, like because it's very niche. There is a lot of research going on, so someone can definitely take this on. And like maybe how these photons are, there are a lot of research ideas to walk to take this field. For example, the communication that researchers took, did physically, was not very long. Like they didn't the message sent was not from Delhi to Calcutta. Like the distance is very small, so why they were able to send, because the quantum computing itself is very niche, right? So we can take this on, and like we can increase the length of the communication signals, and there are also rare earth elements coming in between, and we can also use them, because they have a long coherence time, and the data is not destroyed that easily. As of now, like for example, this superconducting qubits, the data is destroyed, the coherent time is very less. So but there is this thing called rare earth elements, like we can use those to build the information. Then like the coherence time is long, like it's basically photonics, so the coherence time is long, and the data can be it can be stayed in the same state for a for a longer time, so that like it will help. So there are a lot of research proposals and research ideas that people can take from here on in this field. So if someone wants to jump in, then this can be the right time to jump into cryptography and communication. And in India also, IIT Madras, and I have checked the profiles, and IIT Madras and IISER Pune, even they are working on quantum communication. So yeah, they have also like they have also implemented it practically, I guess. I have read it. So yeah, maybe if you are interested, you can go and check their websites. So yeah, so with that I would like to like conclude this session. If there are any questions, I could address. Otherwise, like we can conclude, and we could drop off.
Yeah, thank you, Nandin. Session was good.
Yeah, thank you, glad you liked it.
Thank you. Thank you.